Welcome to everybody who's here online as well. And just seeing everybody here today is great. A couple of empty seats, but that's to be understood, I guess. What I'm going to do probably starting next Wednesday, because we have no class Monday, right? That's Thanksgiving. Friday, remember, is going to be online for everybody. And so what that means is I'm going to be posting sort of a new schedule for Wednesday. The poll I put up initially, like 2 weeks ago, where you sign up for how often you want to come to class in person, does anyone know if you can change your decision? Like go in and put a different answer in? I don't know if you can or not, but if anyone's not happy with their original choice, either do that and let me know, or just send me an email and I can make that. Also, one thing that I wanted to mention too is if you want to do something that's not one of those choices, for example, let's say you want to come every Wednesday and that's it, that works for me too. If that, for whatever reason, fits into your life, I can build a schedule around that as well. It's easy for me. I'm trying to make it so that we don't have empty seats, just because I think there are people who would like to be here that are not scheduled. And if there's empty seats, it's kind of a shame that they didn't get to come. And so what I think I might do is overbook a little. That does run a risk that if all of a sudden everyone happens to show up when scheduled all on the same day, then there may not be enough seats. Although I think like that back table, I could probably get an extra 2. The other thought I had was to have upstairs from where we are right now, sort of the big study room. I mean, technically people could join the class from there, and if there's space, just come down. That's true for anyone who's online right now. Any day that you're not scheduled, you can come and sit in the lounge upstairs and just pop down if there's spaces. Okay, what else is new? We have oral exam coming up. I sent an email around yesterday. I noticed a lot of people right away signed up for a spot, which is great. If you had trouble finding where that was, it's because, remember, we have 2 Acorn sites. We have one that's specific to our section and one that's shared. And the shared one is where all the resources go, all the slides, all the lecture links, and all that kind of stuff. The other one, which is specific for our section, is where I put all of the things that are only affecting us. So rather than try to have 2 sections sign up and have 2 profs and make that complicated, our section's in our section of Acorn. The other section has their own as well. So sign up for a slot. The idea is that they're going to be 10-minute slots. They're all going to be on Teams. So what I'm hoping is I can kind of go bang, bang, bang through the list. I'm planning for each one to be around 7 minutes long. So there's a bit of a buffer in there. I'm not going to try to make it, I don't want it to run late. And it's going to be covering material from the first 3 topics. So we finished topics 1 and 2 already, unit 1 and 2. Unit 3 we started, we'll finish that on Friday. So we'll have an assignment, it's already out based on unit, there's a unit 2 one that's out but not due yet, right? So we just finished that one on Monday. So I'll make sure that the unit 3 assignment is out as well. The first couple of units are kind of short and they move a little bit quicker. So we will be slowing the pace down. The number of assignments or frequency of assignments will definitely slow down as well. All right, unit 2 and 3 are both out. Thanks, Elise. One other thing that I wanted to draw your attention to is the Nobel Prize in Chemistry came out yesterday. Anyone see that? And I have the release right here. It went to Emmanuel Charpentier. I don't know how to, I'm probably not pronouncing that correctly. And Jennifer Doudna, I think is how you pronounce her name. Emmanuel is from France, and Doudna, she's University of Berkeley, is where she works. And they developed a tool you may have heard of, especially if you're in biology, called CRISPR. And it is funny the way the Nobel Prizes in chemistry have gone the last, I'd say, 15 years, is they started out, you know, it was very clearly chemistry work that was getting Nobel Prizes in chemistry. Like people were discovering chemical reactions. They were discovering, this sort of thing. I'd say over the last, say, 20 years, it almost seems to go every second year where it's like a straightforward chemistry discovery. And then the other one is more, I would say, like life sciences, sort of maybe more even biochemistry or biology, but it's more on the molecular side. And that's what this award would be. So this isn't like we discovered a chemical reaction where you mix these chemicals together and this kind of product is formed, which we'll talk a lot about that in the course. This is definitely on the biochemistry side. And what they found was that bacteria have, as part of their sort of bacterial immune system, enzymes which can cleave DNA at very specific points, and it's a defense mechanism against viruses. And they found they were able to replicate the activity of this enzyme and program the enzyme to find specific base sequences and cleave DNA at very specific points. And they could do this reliably. And what they found out then is that they could edit DNA with extreme accuracy and precision. So it's developed a whole. This discovery was only made 9 years ago, 2011. Actually, 2011 is when they discovered the enzyme. 2012 was when they discovered they could reprogram it. And in that period of time, it's dramatically overturned how genetics research is done. And there's a lot of, genetic editing, programming of genomes, and all of this sort of thing that's leading to new therapies. It's leading to new crop varieties, all these sorts of things as well. So, yeah, very awesome. Yeah. I agree with you, Kimberly. Okay, so let's go back to fundamental chemistry, acid-base chemistry. And as I said in class last time, we're going to talk about acids and bases, but not like you've seen it before. Not like in first year where we're doing ice tables, calculating all this sort of thing. You have that already in your mind. You all are experts at this, and I'm sure if I gave any of you a weak acid-base titration to write out on the board, easily start to finish, you could find the pH, right? No problem. We're not doing that here. What I want you guys to have is a more intuitive grasp or a more intuitive understanding of acid-base chemistry of organic molecules in particular. And this is especially important going into biochemistry. I have an example here of a molecule on the screen, ibuprofen. Most of you probably have taken ibuprofen at one point in your lives, or maybe you take it all the time, I don't know. Ibuprofen is an anti-inflammatory drug, also called Advil. Active ingredient in Advil has this particular structure. What functional groups are there in ibuprofen? What's that? Carboxylic acid, right here, carboxylic acid. And as the name suggests, it's acidic. It has a pKa of 4.45. Now, for probably most of you sitting here, I give you that number, that might be utterly meaningless to you. 4.45 may mean nothing different to you than 10 or 20 or 100 or negative 20. So I want you to understand what that number means, okay? So here's some examples for you. First of all, strong acids like HBr, HCl, H2SO4, HNO3. Strong acids typically have pKa values that are negative. Each pKa unit is a factor of 10 of acid strength. So let's say you have a strong acid that has a pKa of -2. Ibuprofen is about 1,000,000 times less strong. Okay, what does that mean? Well, on the other side, water has a pKa of around, well, exactly 14. So this is many orders of magnitude less strong than water. And water can act as an acid. You've all done weak base problems before where water gives up protons, reacts with bases, and makes hydroxide. So we know water can act as an acid. This is much stronger of an acid than water. So the way I think about this is I think about pH 7. pH 7 is a neutral pH. pH 7 is approximately the pH inside of our bodies and inside of our cells. Our blood has a pH of 7.4, so close to 7. Our stomach has a much lower pH, but the rest of our body is pretty basic, slightly basic from 7. So what this means is if an acid has a pKa of 7 and you put it in water that's also pH 7, 50% of that acid will dissociate into its ion and 50% will not, will stay in its form. So another way of thinking about pKa is the pKa is the pH where if you dissolve in water with that pH, 50% is ionized, 50% is not. So what that means, ibuprofen has a pKa of 4.45. If this was in our body and the environment was pH 7, this would be almost completely dissociated and present as this basic form because the pKa is lower. If the pKa was like 9 and it was in pH 7 water, it would be mostly in the acid form. And this is why an intuitive understanding of pKa is important. We need to understand when you see a pKa, what form is this going to be in when it's in a solution with a specific pH? And why does this matter? Well, think about it. You want to take an Advil, you take it as a pill, right? And let's say the pH of your stomach is 1, somewhere between 1 and 2. So you take the pill, it goes into your stomach, it dissolves, you have a bunch of ibuprofen in your stomach. If the pH of your stomach is 2, which of these two forms is ibuprofen going to be in? The left form or the right form?
Left form.
Yeah, the left form. Because if the pH is lower than the pKa, it's not going to ionize. It's going to be present in this form. So why is that important? Well, in order for that ibuprofen to work in your body, it needs to pass across membranes in your stomach and get into your bloodstream. And it works out that species that are charged have an extremely difficult time passing across a membrane. So ibuprofen won't go through your stomach membranes if it was in an ionized form. So because it's low pH in your stomach, it's in its acidic form, it's in its neutral form, can pass through your membranes into your bloodstream, where now all of a sudden the pH is 7.4. So in your bloodstream, which of these two forms is it going to be in? I mean, the other side. So it's a bit like a Trojan horse, right? You're putting it into your body in one form, it passes through the gates, which is the membrane, into your blood, and then it changes forms. All of a sudden now it's in a different, it's in its ionized form, and it'll have a different activity, in fact, the activity that you're looking for in that form as well. So this is something that we see involved in a lot of drug design. You want molecules that can cross membranes where you want them, when you want them, but you don't want things to be ionized in the wrong form, in the wrong part of your body. Yes, question.
Is it possible to explain why they suggest not to eat Advil and
That I don't know. I think that's more around if you, certain drugs, if you take them on an empty stomach, can maybe trigger your body to release enzymes or something that can cleave them. Or I don't really know. It's not for this reason. It's not based on the pKa, based on the acid-base form. Tylenol is not on an empty stomach? Yeah, so I have a question. The ionized one is the active one. Well, yeah, that's the active form in your blood. Yeah. Yeah. Okay. So many functional groups we have can exist in multiple, ionization forms in our bodies. And what I want to do is drill down into why certain ones are more acidic than others. Why carboxylic acids are stronger acids than, say, alcohols, which are up at like pK of 16. So alcohols won't ionize anywhere in your body because there's nowhere with pHs above 16 in your body. Except, actually, that's not true. Sometimes you can have very specific arrangements of functional groups inside enzymes where you can ionize, where you can just have the conditions just right to ionize an alcohol. So enzymes create these very weird artificial environments that can be extremely strong acids or extremely strong bases, but it's just in a very localized, extremely small part of that just one molecule. Eggs. Notice a difference between these two pictures? Kind of. You can see this egg kind of has this kind of jelly border. The other one looks more kind of thin and runny. And this is also something to do with the pH of inside the egg. So when you eat an egg and it's fresh, the egg has a pH inside which is slightly acidic. And what happens over time is the egg off-gases carbon dioxide. There's carbonic acid inside the egg white that turns into CO2 and leaves the egg. And what that's doing is it's slowly removing acid from the egg, and the pH of the white of the egg changes from slightly acidic to fairly basic over a few weeks of the egg aging. And I don't remember the exact numbers. I think a fresh egg has a pH of the white of around like 5 or 6, and an egg that's like 3 weeks old is more like pH 9 or 10. So it goes up like several pH units. And what happens is the egg white is full of protein. And what happens is as the pH goes up, it changes the ionization form, whether it's positively charged or negatively charged, of a lot of functional groups that are on the outside of the egg protein. You know what egg proteins are called? I need someone from nutrition. I forget. Casein, I think, is from milk. Egg white. Anyone in the chat know? Egg white proteins? I forget what they're called. But what happens is when the eggs are fresh and the pH is low, a lot of those ionization states of those proteins are neutral. They're in their acid forms. So when they're neutral, what happens is they can hydrogen bond with other functional groups inside the egg, and they kind of gel together. Like they attract each other. All those proteins kind of hold together, and you can see that this egg kind of has this like solid kind of shape. As the pH rises, as the CO2 leaves, you start to take functional groups like carboxylic acids and turn them into carboxylates. And now you have these proteins that are sort of studded on the outside with negative charges, and those proteins will start to repel each other because they're all repelling ion-ion forces because they're all coated in negative charges. And so what happens is this sort of glob spreads out and it becomes thin, like you see over here at high pH. So, you know, this has a real consequence, the runniness of your eggs. If you become like a really gourmet cook, you have to understand, I think, when eggs are supposed to be best cooked for whatever purpose you're making. I read a book about this once called The Science of Cooking, and it was talking about like, oh, if you're trying to make a, I don't know, oh, okay, we got a oval albumin for egg protein. So if you're trying to make a, I don't know, an omelet, you should have eggs that are this old. If you're trying to make meringue, you need that old, and so on. There's different ages of eggs that are best for different purposes. If you try to hard boil a fresh egg, it's really difficult to get the shell off. And older eggs are better if you want to peel the shell off. But that has more to do with the fact that as the CO2 leaves, water also leaves the egg, and the volume of the inside of the egg, it shrinks as it dries out a little, and that pulls the membrane, the egg, away from the membrane a little bit, and then the shell comes off easy. But if the egg is fresh and it's full, you don't have that.
So could something similar be why you're not supposed to salt your eggs until after you cook them, because otherwise they become runny?
Maybe, yeah. The question was why you're not supposed to salt eggs until they're done being cooked. Yeah, I've never thought about that before. I didn't even know that was a thing.
Yeah, no,
Yeah.
it's, if you salt your eggs too early, they become runny, that's why you get a lot
Okay.
of runny, scrambled eggs.
Oh, good to know. I learn new stuff here, just like you guys do. Okay, so first year chem, we break all acids down into strong acids and weak acids, right? We give you a list of 6 strong acids to memorize in first year. HBr, HCl, HI, H2SO4, HClO4, and HNO3. And it's like, these are strong. And what was the definition we give you in first year of a strong acid? Definition is they completely dissociate in water. Now, that's a bit of a useless definition for us in organic chemistry because we often are not in water. So if you're not in water, if you're in some other solvent like ethanol or acetone or whatever, now how would we define a strong acid? Well, it turns out in organic chemistry, we don't have to fuss too much with this definition just because we have pKa's. We can say much more about how acidic or not acidic something is by telling you what the pKa is. The strong acids that we teach you in first year, by and large, have negative pKa values. So maybe that's one thing that we could say. These are all the strong acids, H2SO4, HCl. You can see the pKa values that are here. There's a couple of others that are borderline. You know, there's no strict definition, like we have HClO3, bromic acid. These are a bit kind of, maybe I'll call them boutique acids. You don't see these used very often, but there's some borderline ones. And we would say that anything else that's got a pKa greater than 0 are weak acids, which the definition of a weak acid is that it only partially dissociates in water. Here's another problem. No acid completely dissociates in water. Take a really strong one like HI, dissolve it in water. It's not 100% ionized. It might be 99.9999% ionized, but not 100. So then comes the question, well, what does 100% ionized really mean? Is it 99% or better? 99.5% or better? So that's just another reason why having a strict definition of a strong and a weak acid it's sufficient. It's great for first year chem. It's great when you're working in water, etc. But in organic chemistry, that definition becomes, I'd say, less important. And it's more important maybe to shift more towards understanding the pKa values. But relative strength is important, and we're going to spend a lot of time talking about relative strength of acids as well. When we're dealing with water, we have another thing I wanted to mention called the leveling effect. You might remember this from first year. The leveling effect just says it's impossible to have an acid in water that's stronger than H3O+. H3O+ has a pKa of minus 1.53. So you can't have an acid that's stronger than negative 1.53 pKa. And why? Well, if you put something like HI in water, to make H3O+. So the HI isn't there anymore. You have iodide and you have H3O+. So strong acids can't get any stronger than H3O+ in water, and you can't get bases that are stronger bases than OH-. And that's a huge limitation. It's actually a great thing for basing biology on water. We can't have these super strong acids or super strong bases existing in our bodies. That's great. They'll just react with water. Water kind of keeps all the acids and bases within a strict range. But it's limiting if you're trying to do chemical reactions where you want stronger acids or you want stronger bases. And because we're not limited to doing chemistry in water, we can have stronger acids than H3O+. And we can have much stronger bases than hydroxide. And you will see lots of examples of this as we go forward in the course. You're going to see bases that are like millions of times stronger than hydroxide. Hydroxide won't be strong enough to do a certain reaction, but we have access to other bases that are stronger. Or vice versa. If you're trying to do acid-base chemistry in water, you can't use stronger acids than H3O+. But if you're using some other solvent, you can use straight H2SO4. We have other acids, we call them superacids, that are millions of times stronger than H2SO4 that we can use to do chemical reactions. Not in water, but in other solvents. So this leveling effect, it's a big reason why water is a great solvent for life. Not always, or often not, a very good solvent for organic reactions. All right, acid strength. What we want to talk about is how can we look at a molecule and understand how strong of an acid it might be. Okay, so we're going to look at a number of factors that play in to how strong an acid is, and I'm going to go through these in order of importance. So the most important factor we're going to deal with first, and we're going to kind of move down the list to the factors which become sort of more subtle as we go through. First one is acids get stronger the weaker the bond gets between the hydrogen and whatever the hydrogen is bonded to. And when I say acids, all through this chapter, I'm talking about Bronsted-Lowry acids. Bronsted-Lowry acids are proton donors. Bronsted-Lowry bases, proton acceptors. Not Lewis acids, not Arrhenius acids, none of those. So compare two acids, HI and HF. What we know is that when you have two atoms that are similar in size, orbitals are roughly the same size. The orbital overlap is really good when these two form a bond, and that bond tends to be quite strong. So CC bonds are quite strong because the orbitals are the same size. HC bonds are also quite strong because the hydrogen orbital and the carbon's pretty small. It's up near the top of the periodic table. They overlap well. But if you take hydrogen, which is really small, and something that's huge, like iodine, iodine has really big orbitals, and hydrogen has really small orbitals, right? So imagine this. We have H and F, both very small, like two mice. They overlap very well. Take whatever you want that to mean. If you have two things that are very different in size, remember, size jumps up by a lot every time you go down one row in the periodic table. So iodine is huge compared to hydrogen. So the overlap becomes very bad. Think of it like this. I'm going to go into notability. If you have a hydrogen and you have, say, a carbon, not a carbon, oxygen, and the oxygen is sp3 hybridized. You have an oxygen, kind of looks like this, right? Pair of electrons, there will be another hydrogen here, pair of electrons, pair of electrons, pair of electrons. The overlap between these two, I mean, the way I drew it doesn't look very good, but it's reasonable. If you look at hydrogen, and I blew it up this time, iodine, I'm going to put way over here. It's got these huge orbitals because it's so far down the periodic table. The overlap percentage-wise is really bad. That causes the hydrogen-iodine bond to be long and weak, where this one is relatively short and strong. So what that means is as you go down the periodic table, we're looking at the atom the hydrogen is bonded to. The furthest down in the periodic table that is, the weaker the bond will be, and the stronger the acid will be. So look at this. HF, pKa of 3.2. So it's, not even a strong acid. Why is it not strong? Well, the pKa is greater than 0. And we said that was sort of our arbitrary line about what was strong and what was not strong. So HF 3.2, going to HCl, -7, -9, -11. These are super strong acids, but HF is not, even though HF is the most electronegative of them all. You'd think it would be pulling the electrons toward itself the most, but it's not because it's small. Orbitals overlap well, and therefore you get a strong bond. So that's the first thing. Look at the atom the hydrogen is bonded to. The furthest down the periodic table it is, the stronger the acid will be. Number two, if we're comparing, let's say, two acids where the hydrogen is attached to two atoms that are in the same row, therefore approximately the same size, and therefore we can't use one to distinguish between any two acids, what we would then look at is just the atom the hydrogen is attached to. And then the acid will be strongest based on whichever atom is most electronegative. So we have HF here again compared to HO, because remember the periodic table goes boron, carbon, nitrogen, oxygen, fluorine, right? So electronegativity increases going this way. If you look at these acids, we have hydrogen attached to fluorine. Fluorine is the most electronegative of fluorine, oxygen, nitrogen, and carbon. So it's the strongest acid with the lowest pKa of around 3.2. Water's not 16, by the way. Water is 14. About 50% of organic chemistry textbooks get the pKa of water wrong. It's actually 14. A lot of them will say it's like 15.7, but that's incorrect. It's 14. NH3 is a really weak acid. Super high pKa means it's a super crappy base. You can't remove an H plus from NH3 unless you can get to a pH greater than 36. Right? You can't do that in water, but you actually can do that in organic solvents. This is approximately 55 for CH4, an extremely crappy, like extremely weak acid. And that's just approximate because people can't reliably make it in solution, so this is based on estimates. So yeah, you only go by the electronegativity if you're comparing acids where the hydrogen is bonded to elements that are in the same row. Therefore, they're the same size, and you can't use one. So just comparing these two, what we see is that acids become stronger as you go left to right, and stronger as you go down the periodic table. All right, often we're comparing acids, though, which are what we call OH acids. Those are the most common acids, where the hydrogen is attached to an oxygen atom. So sulfuric acid would be an example of an OH acid, because the hydrogen is bonded to an oxygen atom. Same thing with alcohols, same things with carboxylic acids. Most of our strong acids, not HCl, HBr, HI, but all the other ones are OH acids. And definitely they're the most common kind of acid you'd find in a biological molecule. What we find is that acids are stronger if they make anions after they lose H+, they make anions that are resonance stabilized. Right? If you can make the anion have resonance structures, that's going to cause the acid to be stronger than if the acid does not have resonance structures. So we use this criterion when we're looking to compare acids that you have the same atom. So you can't use rule 1 or rule 2 to define which one's a stronger acid. I'm going to skip that one. The way I'm not really happy with the way I drew these. Look at ethoxide. Ethoxide is CH3, CH2, O minus. Compared to acetate, which we've seen a million times now. This has a resonance structure. Nope. This, no resonance structure. So this comes from acetic acid. This one comes from ethanol. pK of acetic acid is around 5. pK of ethanol is around 16. 11 orders of magnitude. That's a 1 with 11 zeros behind it. That's how much stronger of an acid acetic acid is down here compared to ethanol. Why? They're both OH acids. They both are acids where the hydrogen is on oxygen. The difference is that acetic acid makes an anion that has a resonance structure, and ethanol does not. Why does that matter? Well, that ethoxide is stabilized because the charge is spread out, right? It's delocalized, we say, over 2 atoms. Spreading out the charge makes that charge much easier for the molecule to bear, right? Think of a charge as almost like a burden for a molecule. And let's say like you have a burden. You're trying to like lift a piano on your back. Well, you know that lifting that piano is a lot easier when you have 2 people. And it's even easier when you have 4 people. And trying to do it all yourself is very difficult. So for the ethoxide here, you have this charge all stuck on one atom. It's a nice electronegative atom, so we have that going for us. But still, that's not going to be anywhere near as easy for that molecule to bear as the acetate, where it's split evenly over 2 atoms. So resonance is the next thing. The fourth is, let's say they're equal in terms of resonance structures. How do you compare them after that? Well, you look for nearby what we call electron withdrawing groups. Or another way to say that is nearby electronegative atoms. So if it's an organic molecule that has maybe not attached to the hydrogen, but close by electronegative atoms like fluorine, like chlorine, like oxygen, like nitrogen, they can cause the acid to be stronger a few bonds away. So I'm going to show you an example of this. Here's acetic acid, which we know is a pK of 4.75, and then chloroacetic acid. Basically the same molecule, except we're putting a chlorine where the CH3 was. Right? We're adding a chlorine, we're replacing a hydrogen with a chlorine. That causes the pKa to drop about 2 units. That means it's about 100 times stronger. Just by adding that chlorine there. Well, why is that? Well, we know the anion, when it forms, is this, with a resonance structure. You can't draw a resonance structure where you're putting charge on the chlorine. But the chlorine has another thing it can do. It can't stabilize this charge by resonance, but it can stabilize the charge by something called the inductive effect. What that means is that you can have an electronegative atom like chlorine that will form a polar bond, like the one I just drew, that will kind of cause this carbon, where the chlorine is attached, to be positively charged, electron poor. That can kind of induce a dipole in the next bond and induce a dipole in the next bond. So what that chlorine is doing is sort of pulling electron density through all of the sigma bonds in towards itself. So it's helping share a little bit of that negative charge that's formed when you'd remove H+. Fluorine would do an even better job than chlorine because it's more electronegative. So if you replace the chlorine with fluorine, the pK is going to drop again. Or if you put 2 chlorines or 3 chlorines, they would have a stronger effect than a single one would. So we call this the inductive effect. If you have electronegative atoms nearby, they will help stabilize. And you can see this sort of chain of bond dipoles that can be formed inside of a molecule. Has the effect of just sharing negative charge. Alkyl groups do the opposite of electronegative atoms. Alkyl groups like ethyl, methyl, they actually push electron density. They don't pull. They're not like an electronegative atom. They're more electropositive, and they push electron density. So if you look at the acid strength of these acids, formic acid, acetic acid, propionic acid, the pKa is actually increasing. They're becoming worse acids the longer that alkyl chain is, or the bigger that alkyl group is. And that's because it's getting better and better at pushing electron density into that carboxylic acid. The best one is formic acid because there's nothing pushing any electron density in, but propionic acid is the worst. It's pushing quite a bit of electron density into that acid, which makes the anion less stable because you're building up more charge into that part of the molecule, and it wants the opposite. It wants to spread that charge out. It wants to get rid of some of that charge if it can. I don't have it here, but one thing I should mention is if you have, imagine you have a molecule that looks like this. Okay, you have an electronegative atom near the carboxylic acid, and we're going to compare that to something like this. Which one of these do you think is a stronger acid? A or B? Yeah, A is going to be a lot stronger. And that's because it's much closer. There's fewer bonds that fluorine has to act through to pull electron density away. This fluorine, you know, like you'd have to go through like, I don't know, a dozen bonds or something. Well, not a dozen, but you know what I mean. A lot of bonds. And every bond it goes through, the effect becomes weaker and weaker and weaker and weaker. And in fact, this molecule may not be much more acidic at all than the same compound with no fluorine there. How about something like this? Which one of these two is stronger, A or B? I heard B. A. Yeah, A is stronger because you have two electronegative atoms, two fluorines, both pulling charge out of the carboxylic acid. Help stabilize, yeah. So A is the stronger of the two acids. I'm going to do one more example. Cl. Br. A or B, which one of these is stronger? I hear A's and B's. Correct answer is A, because chlorine is more electronegative than bromine. So there's sort of three effects here. How many electronegative atoms there are, how nearby those electronegative atoms are, and how electronegative those electronegative atoms are. Okay, the last one, and this you typically only see when you're dealing with carbon, is hybridization can affect the acid strength as well. So this pops up probably only once in this course, where if you look at these three, ethine it's a alkyne. What is the hybridization of the carbons in ethine? Yeah, these are sp. How about ethene? These are sp2, both of them. And ethane? Yep, sp3. And look at the pKa difference between those. 25, 44, and 50. Basically, these are so high, it's basically next to impossible to deprotonate them. We don't really have bases that are strong enough to pull hydrogens off of sp2 or sp3 hybridized carbons. But we definitely do have bases that hydrogens off of ethine. And we'll be doing reactions where we treat what we call a terminal acetylene with a strong base. We can pull that hydrogen off and make this anion. And that anion can become a very strong acid. The reason why sp hybridized atoms are much more acidic than sp2 or sp3 is because if you look at the hybridized orbital, sp, we would say that it's 50% s and 50% p. Okay, fair enough. It was made from a 1s and a 1p. The s orbital is centered on the nucleus, right? So what that means is that by having a lot of s character, that sp orbital has the electrons in that orbital close to the nucleus a lot of the time. That's a stable place for electrons to be, because they're negatively charged, the nucleus is positively charged. If you have, say, an sp3, it's only 25% s, and it's 75% p, because there's 3 p's and 1 s that went into that orbital. So the electrons aren't as close to the nucleus, they're not as stable, which destabilizes anions like this. So this anion is stabilized by having a lot of s character that draws the electron pair closer to the nucleus more of the time. So yeah, that one doesn't come up super often, but it does come up in the case of carbon. Oxygen, we'll never see it. Oxygen, we never look at different hybridizations of oxygen as acids. I don't think, maybe not in organic 1. All right, so to finish you off, I have a very long list of acid strengths. This is a table that we typically post for you on midterms, exams, things like that. And so what you see here is sort of a list of approximate pKa values for a bunch of different acids. You can see this guy up here, HSBF6. What's that? So you take HF and you mix it with antimony pentafluoride and you get this thing. That's called, it's got a name. It's a superacid. I think it's got a special name though. Nobody really knows exactly what the pKa is. It's less than 12. I think it's been published as around -26, which makes it like basically it'll protonate anything else. It's difficult to make. It's difficult to store because it'll eat through glass like it's nothing. You need special materials to contain it. Then we have sort of the regular strong acids, HI, HBr, HCl, H2SO4. This one, which is an organic version of sulfuric acid, which I think we'll use, toluene sulfonic acid. I think that's just. Then we have a couple of things which don't look very familiar. We will be using many of these acids and bases in the course, and it's handy to always be able to refer to what their pKa values are. And look at the huge range. pKa of 50 to pKa below -10. And every single unit is a factor of 10 in acid strength. There's a huge range. And we can access them all because we're not stuck in water. If we're stuck in water, you're kind of here. You can only deal with acids in that kind of a range. But when you go outside of water, they're all accessible. And we will be accessing, well, maybe not every one of them, but many of them we will see. Okay, it's 9:20. Let's just do one example before I let you guys go. I'm going to keep you for 2 minutes. What is the strongest base? When you see a question like this, what I like to do is turn it around, because I like to think of things in terms of acid strength, not in terms of base strength. So I would look right away and I'd say a stronger base equals weaker acid. So I'm going to flip this around. I'm going to turn all of these things into acids. This becomes HF. This becomes NH3. This becomes H2O. This becomes CH2FCO2H and HI. And now what I want to do is find the weakest acid out of all of these. That's the same thing as saying what is the strongest base of all those conjugate bases. So how do we rank these? We go one by one through those 5 factors that we looked at, where the top factor was the size of the atom the hydrogen is bonded to. So if you look at the periodic table, remember it's B, C, N, O, F, Cl, Br, I, sulfur, you know, it's other atoms in there. If you look at A, B, C, and D, the hydrogens are all bonded to atoms in the first row. But E, H, I is way down here. So what's going to be the strongest acid out of all of these? HI, by a long shot. According to our first rule. By the way, this CH2FCO2H is FCH2COOH. So now looking at them, we have HF, NH3, H2O, FCH2OH. Okay, so which of those is going to be strongest? We can't use rule 1 anymore because all those atoms the hydrogens are bonded to are in the same row. So we go to the second rule where we look at the pKa. Sorry, we look at the atom the hydrogen is bonded to. And we look at the one that's most electronegative. So we have fluorine, we have nitrogen, oxygen, oxygen. Which of those is most electronegative? Fluorine. So the second strongest acid we would guess is HF. Next we have nitrogen, oxygen, oxygen. So what's more electronegative, nitrogen or oxygen? Yeah, oxygen. So oxygen, we expect C and D to be stronger than B. So 5 is going to go to B. It's going to be the weakest. Weakest acid, strongest base. So we have some middle ones. We have OH minus and 1. We can't use rule 2 because they're both bonded to oxygen. So we go to rule 3, which was resonance structures. Does either of H2O or this guy make resonance structures if you remove H+? Yeah. This one makes resonance structures. It's a carboxylic acid. So it's going to be stronger than C. So we get our ordering like that. So that's of increasing. So 1 is the strongest acid and therefore the weakest base. The weakest acid is NH3, therefore the strongest base is going to be NH2- out of that list. So these are the sorts of questions we will probably be giving you, or we will be giving you, from this kind of a unit, where you have to be able to look at those 5 factors and compare a list of acids and bases and sort them into the strongest and weakest. This question, by the way, becomes very easy if you have a table like this and you find them in the table. Because look, we have HF is there, HI is there, NH3 is there, water is there, and the other one was, no, it wasn't this, and it wasn't this. It was, so yeah, we're missing 1. But yeah, you should be able to apply those rules. Okay, we are done for right now. We're going to meet again online on Friday, same time, same place. And I feel like we're almost kind of done this unit, but we'll do a bunch more practice and we'll go from there. All right, see you everyone.